challenges, right, in the traditional image segmentation algorithms, and what are the future prospects of this. So here's the outline of this talk, right? So I'll start with I'll start with discussing something called as what do you mean by image segmentation and how to cast an image segmentation problem as a pixel level classification problem. What are the different types of image segmentation we have? I still remember that some of you have some of you have has asked one question, that what is the difference between semantic segmentation and instance segmentation. We'll see today, right, how we can differentiate semantic segmentation with instance-based segmentation. And there's one more variety of segmentation we have called as panoptic segmentation. We'll see. And also, we'll see why we're interested in convolutional neural network based or deep learning based segmentation approaches. We have also some traditional, right, low level image processing techniques through which you can solve segmentation problem. But why we are preferring? Because we have seen the success of the convolutional neural network over the years for solving a variety of computer vision tasks. So especially I'll be touching upon several popular convolutional neural network and vision transformer based models, right, that have been dedicatedly designed for solving image segmentation task. There are two case studies I will show you, right? I mean, there are a few approaches which we have developed recently for solving medical image segmentation task. And at the end, I will talk about, right, some of the challenges we face and how to overcome those kind of challenges, right? So whenever you are having any doubt, you can just stop me or you can just write your query, right? I'll try to answer you, right, during the session. Fine. Okay. So let's start with image segmentation, right? What do you mean by image segmentation? You might have seen it, right? Applications, or you
Hello,
might have seen
sir,
this type of images, right? Since last 2, 3, 4 or 2 to 3 days, right? So when I say image segmentation, it is nothing but partitioning the image or video frames into multiple segments and objects. And here you can see some of the outputs. These are the input images you can see over here. So let's say this is an input image and this is an output, segmented output image, where you want to only focus on, or where you want to only highlight the objects, which are nothing but in this case a person and there is a bike. Similarly, in the second picture, if you look at here, so I want to only highlight this part, right? I want to partition this basically, right? I want to highlight, let's say, this region, right, where there is an aeroplane. So given this image, I want this kind of image, right? I'll talk about it, how we can solve this problem with the help of deep neural networks, especially convolutional neural network based models and vision transformer models. You'll find its applications everywhere, starting from autonomous vehicle, right, where sometimes you need to even detect pedestrians, right? Even in video surveillance also you will find its applications, scene understanding, and mostly you will find its applications in medical image analysis. So I'm saying like this because you will find there are a couple of popular algorithms that have been developed over the medical medical imaging domain first, and then it has been adapted to traditional computer vision kind of problem statements, right? So we'll see in details how can we, define this image segmentation as a classification task, right? And how to solve this is using convolutional neural network. Before I discuss, right, how we can define image segmentation problem as a pixel level classification task, let's also discuss one interesting thing, the difference between classification with localization, object detection, and image segmentation, right? These are all important tasks which can be solved using the modern days deep learning algorithms. So let us look at this example, right, first. This is, let's say, the input image which is given to us when there is a cat in the image. Classification will tell us what is in the image. That means, given this image, you can just assign a label to this particular image, which is nothing but cat, and that is a classification task. And what it tells, what is in the image. Classification with localization means what is in the image, you have to assign a label, at the same time where it is, that means where the object is present, for which we are getting a class level, which is nothing but cat. So we need to also provide a bounding box over here. That is classification with localization. So then what is object detection? Object detection, you can just look at this example. What are all the objects that are present in this image? So you need to provide a bounding box, right? And where are they exactly? That means you need to provide first what are the objects that are present and where they are. You need to also provide the bounding box. That is what is object detection. But what do you mean by then segmentation? And how it is different from object detection and localization? So in case of semantic segmentation, given this image, now you look at the output over here. So semantic segmentation tells here is what type of object is each pixel on the image. That means you want to classify here every image either into grass category or into cat category or into tree category or into sky category. So there are 4 classes over here, right? So you need to assign a semantic category to each of the pixels that are present here. So it will give us a lot of important information because from the bounding box, you may not get the exact boundary of the object, but from this segmentation results, you can see over here, you may get the boundaries, and there are several other informations you can find out using segmentation or using semantic segmentation. And there's of course a difference between semantic segmentation and instance-based segmentation. I'll explain not using this example, I'll explain with another example where you can easily understand what is the difference between semantic segmentation and instance-based segmentation. Instance-based segmentation also differentiates among the objects of the same class. Let's say, for example, right? Let's say this is one, this is one particular type of image is given to us, right? Semantic segmentation doesn't care about the type of object, right? It will not create any difference among the dogs. But instance segmentation will say this is dog 1 or this is dog 2, right? But instance segments for semantic segmentation, all are like dogs, right? It doesn't create any difference among the objects of the same class, right? That is what is the major difference between semantic segmentation and instance segmentation. I'll also explain with another example. Let us now try to define what do you mean by semantic segmentation and why do we, right, prefer convolutional neural network or deep neural networks, especially over the traditional segmentation algorithms we have. So this is, let's say, an input image, and this is the output image. Output segmented image. That means here in this case, you can see I want to only highlight the objects. I want to highlight or group those pixels where there is person and where there are bicycles. Now you look at the output here, right? So these are the pixels where person is there, and these are the pixels where bicycle is there. When I look at the second person, also same thing, but we are not here differentiating among the persons. So differentiating among the persons is nothing but here known as instance-based segmentation, right? So this is semantic segmentation where your group is to, where your basically task is to group similar types of pixels in an image. So while I'm saying that grouping similar type of pixels, it can be casted as a pixel level classification problem. What do you mean by pixel level classification problem here? That means for every pixel, you will assign a class level over here in the output segmented image. So here, particularly for this case, there are actually 3 classes, although we know, yes, there are 2 classes, that is person and bicycle, but we need to also consider always, right, an additional class, which is nothing but known as background class. Either the pixel will belong to the person category or the pixel will belong to the bicycle category, or else the pixel will belong to the background category. So this whole semantic segmentation problem can be now casted as a pixel level classification problem, where every pixel can be classified into either of these 3 categories. I hope it is clear, right? But we don't want to solve this type of problem with the help of traditional segmentation algorithms which we have. So traditional segmentation algorithms may include thresholding, which you might have seen in image processing. K-means clustering is also one of the unsupervised technique, which is very, very popular for image segmentation task, but not for the complex image segmentation task. where you need to also decide the K value, the number of clusters initially. Maybe in this case, it is 3. But you may face a lot of difficulties while solving the problems. You may not get, or you may not get the output, right, which will meet the expectations of the real-time scenario. So what we are interested in is learning-based segmentation problem, right? That means as we have tested it, right, as a pixel level classification problem, so we can just have X, and we can have Y here, and then we can learn a function, f of x, right? We can learn a function which can map from x to y. But in case of conventional classification problem, x is nothing but an image, y is just a level. But in this case, x is an image, y is also an image, right? Y is also an image. You can see over here, this is x, this is y, right? You know that, yes, labeling or annotation is always a costly process, even for a classification task where only you used to assign a single level by looking at the image. But here you have to level each and every pixel. And that is why it is written, these type of techniques or learning-based semantic segmentation, although accurate, but also quite annotation intensive. We need pixel level annotations. For every image, we need this kind of mask or pixel level annotations. Then only we can think of designing a model which is f of x, which can map from x to y, right? So that is why, I mean, if this kind of images are not given to us, you cannot solve this problem, right? I'm not going into the details of, I'm not discussing here about here the unsupervised techniques or like say semi-supervised techniques. We'll discuss later on, right? So I'm talking about only supervised based semantic segmentation problem, supervised learning based semantic segmentation problem, where we need X as well as its corresponding Y, which is of course a mask, or you can say pixel level annotated image. Very, very difficult for a person to annotate. It is of course a time consuming task, right? And if you're dealing with a medical image, so all pixel has to be right correctly what I can say annotated, which will take a lot of time. It will consume a lot of time, right? And we know that, yes, of course, the clinicians, especially the doctors, are really busy. So for them, it is very, very difficult even to annotate 10 image, right, per day. But still, we are interested in solving the problems because it is accurate and it mimics the human vision system, right? The way we learn by looking at the images, where is the object, what are the boundaries of the object, we want to solve in the similar manner. So that is why we're interested in the supervised learning based semantic segmentation problem, which can be casted as a pixel level classification problem. I hope the concept of the semantic segmentation is now clear. Now I'll show you one example through which you can easily find the difference between the semantic segmentation, instance segmentation, and there is something called as a panoptic segmentation, which is nothing but just a union of semantic segmentation and instance segmentation. So you can see over here, in case of semantic segmentation, you are assigning a semantic category to each of the pixel that is present in the image, and if those those belong to same category, like person category, you are not differentiating, you are only assigning it as same semantic category to all the persons. This is a person, this is also a person, right? And for vehicle, it is nothing but same, right? We are assigning a similar semantic category to each of the vehicles over here. But in case of instance segmentation, we don't care about others. We are only caring about the objects, which are very much important for us. And again, we are trying to differentiate between the objects of the same class, which is person. Here it is person 1, person 2. It is vehicle 1, vehicle 2. But in case of semantic segmentation, you were simply considering all the vehicles, right, is nothing but one category, that is vehicle category. And you have also assigned a semantic category to all the pixels that is present in the image, but we are not at all interested in this. Now you can see the panoptic segmentation, which is nothing but the combinations of the semantic segmentation and the instance segmentation. I hope it is clear that the difference between the instance segmentation and the semantic segmentation. You can relate with your problem statement, right? I don't know, I don't remember who has asked this question, but I've seen these questions multiple times, right, in the chat box. Yeah, these are some of the traditional segmentation algorithms like thresholding, watershed, graph caught, region growing, and k-means clusterings. These all are like unsupervised, right? These algorithms do not need this mask to solve the problem, and that's why it is not accurate, right? You can say like this, right? So we don't actually follow this kind of this kind of algorithms nowadays because they are not that much accurate on the complex scenes. We are interested in learning the segmentation models, but although we know that it always demands huge amount of data along with its corresponding mask, which is even complex to obtain. Now we'll see the evolution of the convolutional neural network and vision transformer based models that has been used for image segmentation. Like for image recognition or image classification, you have seen, right, LeNet in 1998, right? This is the first architecture. The CNN concept is not at all new, right? It has been, the first architecture was actually designed in late 80s, but ultimately published in 1998. The second architecture was nothing but AlexNet, published in 2012 by Professor Hinton, who has developed the backpropagation algorithm, recently been awarded Nobel Prize because of his huge contribution towards the field of neural network and convolutional neural network. So AlexNet, the designer, or you can say the developer of the AlexNet, has won, right, the Nobel Prize this year, right, Professor Hinton. So very, very powerful architectures, convolutional neural network and all, right? He has also developed capsule network, several other autoencoder concepts. He has given a lot of concepts he has given, right? And AlexNet is the major breakthrough actually, right, in the field of convolutional neural network, because there is no development. If you'll find from 1998 to 2012, there is no development in the field of convolutional neural network, right? But after 2012, you will find, right, the developments of the CNN and several such, right, advanced deep learning algorithms, including vision transformer and so many things, so many other architectures, right? So then you might have seen something called as VGGNet, something called as GoogleNet, InceptionNet, ResNet, DenseNet, and the latest one is nothing but called as, I think, DenseNet, MobileNet. MobileNet is also very, very important. EfficientNet. There are different types of architecture you will find, right? If you go through the literature, these are all like the winners of that particular challenge, ILS VRC, right? And you will find. So all these architectures are in this. Particularly, this ResNet and DenseNet are very, very popular. Even MobileNet is very popular because it is a lightweight architecture, right? You will find a lot of different kind of contributions in these architectures. It's not like they have only included more number of layers and they have got the papers and they, it is very, very popular because of the large depth, or you can say the depth is more in on all these architectures. It's not like that. So there are a lot of new contributions you will find in these architectures, right? In residual connection, you will find the residual connection they have introduced for several different purposes. Similarly, you will find the uses of dense connections in DenseNet. In the MobileNet, you will find how to reduce the number of parameters with the help of depth-wise convolution. I've already mentioned that there are different types of convolution operations people have proposed over the years, including the across convolution, depth-wise convolution. There are point convolution, different types of convolutions, deformable convolutions people have proposed over the years, and these depth-wise convolutions, right, are very, very important. Fine. So we will also find that what is the uses of this depth-wise convolution and all, right, in MobileNet papers. Separable, there is something called as a separable convolution, right, which is also very, very important. So you can also think about using this separable convolution. You will see how we have used the concept of separable convolution in one of our contributions to reduce the number of parameters, right? Like we have evolution, right? We have developments in the field of convolutional neural networks for solving classification problem. We will also find, right, the evolution of convolutional neural networks in vision transformer based models for solving segmentation tasks. So you can see the very first architecture was proposed in 2014 is known as fully convolutional network. So we'll discuss some of these popular architectures which I've listed over here. And there's another architecture which is still now popular, right? From 2015, if you go through this paper, you will find this is the most popular architecture till date, and almost all the new segmentation architectures are based on the architecture, based on the design of this unit architecture. And this was originally published in a conference known as MECI, which is a medical top tier medical conference. And this particular architecture was first built on the medical data set. You can see over here, right? These are medical data sets. So that's why I mentioned, right, in the first slide itself, that image segmentation has, right, or has been extensively used in analyzing the medical images, so especially for medical image segmentation. At the same time, you will also find another architecture known as SegNet, followed by PSPNet, DeepLab, and then you will find a lot of variants of UNet architectures. Lot of variants, including Rush Unit, Dense Unit, Unit Plus Plus, Unit Triple Plus, Rush Unit Plus Plus, and there are so many architectures you will find in the literature, which are nothing but called as the variant of the UNet architecture. You will also find there are also unit-based architectures based on, you can say, the concept of transformer that has been designed over the years, like unit or transunit. I'll also show you some of the transformer-based architectures right today, including some of the popular convolutional neural network architectures. Let us first discuss, right, the architecture of the first semantic segmentation, right? First architecture which has been designed for solving semantic segmentation problem. That is fully convolutional network. Why the name is so called fully convolutional network? How it looks like, and what is the difference, right, between this architecture and the architecture which you have seen earlier, which are used to solve classification problem. Now, if you look at this particular right architecture, it looks like the architecture which you have just now seen, right? That is what is known as VGGNet. This FCN, fully convolutional network, adapts various classification networks, right, especially VGGNet and GoogleNet. And this is actually an example of a VGGNet architecture, where you have seen that VGGNet contains 3 FC layers at the end, and each of the FC layers containing 406, 2 of the FC layer containing 4096 number of neurons, and the last FC layer contains 1000 number of neurons to solve a 1000 class classification problem, right? Because it was originally designed on ImageNet dataset, which contains 1000 number of classes. So the name itself says here fully convolutional network, right? But in VGGNet, there are 3 fully connected layers. So what they initially, right, did is they replace all the 3 FC layers by 1x1 convolutional layers, right? So there is no FC layer now. All layers are now replaced with 1x1 convolution, and the last 1x1 convolution will be having C plus 1 number of channels, right? That means it is not going to have the neurons equal to 1000. It will be having C plus 1, where C denotes the number of classes, and 1 is nothing but for the background. 1 is for the background class. So particularly for the problem statement on which, or the data set on which this FCN was developed, contains 20 classes, including 21 classes, including the background. That is 20 classes plus 1 background class, 21. Right? So then what basically they did, they replace all these layers into 1x1 convolutional layers, and the last layer, if you look at here, now contains 1x1. Sorry, the last layer contains 21 number of channels. Right? That means the dimension, the final dimension of the last one is nothing but 21, because there are 21 classes, and your goal is to actually classify each and every pixel of the image either of these 21 categories, right? But there is a problem here. Can you see some problem over here? What do we know? That in case of segmentation, that yes, the input resolution, that means the output is always an image. The output is not a set of probability values, which we have seen in case of classification. The output is nothing but here is also an image. The input is an image. And the output resolution should be same with the input resolution, because what you are doing, you are simply assigning a label with respect to each of the pixels of the input image. But what you have seen in these architectures, that you are using max pooling operations, or you are using pooling operations, which are nothing but downsampling operations, for which what you are getting at the output is nothing but a very small dimensional feature vector. From there, that means what we are observing here is that you are only applying downsampling layers. But what you are planning to do here is your expected output should be nothing but an image. What is the solution here? The solution is nothing but to apply upsampling operations, right? Solution is to apply or to perform upsampling operations to get back to the original image resolution. So we know there are multiple ways to perform upsamplings. There are different types of interpolation techniques which we discussed also, right, in the initial lectures, that we have different types of interpolation techniques, including nearest neighbor interpolation, bicubic interpolation, bilinear interpolation. But we are not interested in those kind of interpolation techniques. What they have introduced in fully convolutional network, upsampling operation, right, is nothing but, that means from here to here. That is nothing but called as transpose convolution. I don't know how many of you heard about this term. Transpose convolution or op convolution. Deconvolution is not exactly the perfect word which can be used over here. It has some separate meanings in signal processing. Transpose convolution. What we have seen yesterday or day before yesterday, that whenever you are applying a kernel or whenever you are applying a convolution operation over an image, so the output, whatever you are getting, right? Let's say you are not using any padding over here, and whatever the output you are getting is nothing but called as, let's say you are using 3x3 filter, the output is nothing but a reduced version of the original input. So this will be the output after performing the convolution. So that means convolutions also help in reducing the dimension of the input, right? But we need here such an operation which will do, right, the reverse thing, whatever the convolution is doing over here. That means if you perform convolution over an image, the size has to be enlarged instead of reducing the size. Here 254 was 254. I want to enlarge the size after applying the convolution operation. And that is what is actually transpose convolution. And why do we prefer this kind of upsampling operation? Because this upsampling operation is also learnable. Right, the kind of upsampling operations which we discussed just before, those are not learnable. You'll not be having any coefficients, will not be having any weights and bias associated with it. So that means whatever you have done is correct or wrong, you don't know. So you want to just make it learnable. We need the reverse operations of the traditional convolution, which is known as transpose convolution, which helps in enlarging the size of the input image. I hope it is clear. Please try to go through the details of the transpose convolution, right? I mean, you can consider a one-dimensional signal or two-dimensional signal, apply the transpose convolution, then you check how it is helping in improving the size, or you can say in enlarging the size of the input. And this is what is followed, right, in FCN. And then finally, after applying the upsampling operation, you can see over here, there is a feature map here at the final layer, which which contains 21 channels, and this size, especially the height and width, is of course the same after upsampling operation, but the channel is 21 here. This is the actual output of the model. From this output, you need to predict this particular mask. What basically it gives us, right? It has 21 channels. That means for every pixel here, you will get 21 number of values, right, across the channels. And what are these 21 here? The first channel will say class number 1. The second channel will denote the class number 2. And maybe the last channel will denote the background. So that means, again, you will check that these are all, again, the probability values. And you are now looking at the probability values across the channels. And you are checking the maximum out of them. That means, let's say the third one, let's say the first pixel belongs to the background. You can see over here the first pixel background. So that means the probability value, right, of this pixel with respect to the last channel, that is 21st channel, is going to be high. And based on that, you can just provide a color coding over here that yes, this is nothing but a background. So then next, you want to classify the second pixel. The second pixel, for the second pixel, you will also find the maximum value with respect to the last channel, because second pixel is also a background pixel. Every time you will get 21 probability for every pixel right? You will get 21 probability values, and out of the 21 probability values, you will only check the maximum probability value, and accordingly, you will assign the class level for each of the pixels. So the similar kind of, the loss function you can apply over here, the kind of loss function which you have seen earlier. The kind of loss function which you have seen yesterday is known as cross entropy, right? Which was computed class-wise, if you remember the formula. But here you will compute the sum of the pixel-wise cross entropy. For every pixel, you will get error. And then you can find out the sum of the errors. You can call it as sum of the pixel-wise cross entropy error or cross entropy loss function. And that is the simplest or most widely used loss function in the semantic segmentation learning setup. I hope it is clear, right? Why do we need 21 channels, or why do, and it is always possible only by using a 1x1 convolutional layer at the end. Whatever may be the size of the last convolutional layer. So what you can do, you can just apply a 1x1 convolution, and through which you can reduce the dimension of the feature, dimension of the channel from any dimension to C plus 1 dimension, where C is nothing but the number of classes which you are having. I hope it is clear. So this concept will remain same across all the networks or across all the architectures. But what limitation we have in fully convolutional network is we have only used one upsampling layer to get back to the original image size, right? So this actually creates sometimes problems. So instead of only one layer for upsampling, can we have multiple layers of upsampling? That is what is the research gap people have identified at that time. And then you will find a couple of architectures which are known as encoder decoder based architecture. Segnet, right, comes first as a first encoder decoder architecture. Actually, it comes at the same time when even UNET also was designed, right, in 2015 onwards. So Segnet is nothing but known as the encoder decoder architecture. You can see over here, right? So this part is known as encoder, and this part is known as decoder. So decoder is exactly the mirror of the encoder. Why do we need this decoder? We'll discuss, and why it is better compared to the fully convolutional network. This encoder, right? This encoder could be, right, any classification network which you have seen, like VZZ, Google, it can be any network. So what they have considered is VZZ without FC layers. They're not considering any FC layer, the 3 FC layers. No need to even convert those FC layers into 1x1 and all. Just drop all the FC layers, and whatever you are having, right, in VZZ can be considered as an encoder layer. And what we know that in VZZ, we are using a lot of max pooling operations, right, for downsampling, or you can say for reducing the dimension of the feature map. So now the thing is, how we can design the decoder in this case. Decoder, as I mentioned, is nothing but the mirror of the encoder. Now the thing, how then the upsampling is performed over here. In Segnet, there is nothing called as, there is nothing called as transpose convolution used over here. Rather than how they performed upsampling operation, instead of using the transpose convolution, which demands parameters because it is a convolution operation and it is learnable as well, what they did is they just stored the winning pooling indices at each of the pooling layer. Right? What does it mean? What do you mean by winning pooling indices? Let's say you are applying the pooling 2x2 pooling operations over this image, right? Like this. This is a 2x2 pooling, right? Let's say you are applying like this, and you know that while applying max pooling, right? So this pixel was having highest value, and you will just store its index. And in the second window, this is going to be, this is going to store the best value. This is going to store the maximum value. So like this, you need to store the winning indices. right? While performing the downsampling operations or mixed-pooling operations during the encoding process. In the decoding process or in the decoder, you can use these winning indices, right, to upsample the image, followed by some of the convolutional layers, like you have seen in BGG. Many convolutional layers followed by one max pooling layer. So similarly here it is upsampling layer by storing the pooling indices followed by multiple convolutional layers, because you are going to get a sparse kind of feature map after applying this upsampling operations through saving or storing the winning pooling indices. I'll explain you with an example. You can see over here. Let's say this is one output map which is given to us, right, in the decoder stage. In any decoder stage for which you want to upsample from here to here. So how to upsample? So this is the indices which you have stored, right, during the encoding process. That means from encoder you can consider these max pool indices. You can see over here for this particular A, right, it is the winning indices was 0 0. So this is 0 0 position, this is 0 1 position, this is 1 0, this is 1 1, like this, right? So for B, the winning indices was 1 0. You can see over here, this is 1 0, this is 0 0, 0 1, 1 0, 1 1. So this one, right? For D, you can see for C, it is again 1 0. So this position. And for D, this 0 1. 0 1 means this position. And the rest other values will be 0. That's why I said that you are going to get a sparse feature map during the decoding. But again, you have to use a different convolution operations over there, right? So the decoder uses pooling indices of the corresponding max steps to perform upsampling. That is what I discussed. And these sparse upsample maps, you can see over here, sparse upsample maps will be passed through some of the convolutional layers to produce dense feature maps. Very, very important. Why we are using convolutional layers, right? So same number of convolutional layers, same number of stages in the decoder, similar to the encoder. And finally, you will find a 1x1 convolutional layer at the end, right? That is going to be your segmentation head. Finally, you will be having a 1x1 convolutional layer having 21 channels, right? If you are solving a problem where there are 20 classes and one background class, and this will ultimately give you the size, right, of the size. The spatial size is going to be same as the input size, and the depth is going to be 21. And based on the maximum probability value, you can assign a level to each of the you can assign a semantic category to each of the pixels we have in the input image. So that is how actually the SegNet, right, was designed. At the same time, the architecture, which is not a unit architecture, was proposed in a medical conference known as MICAI in 2015. So in this unit architecture again is nothing but an encoder decoder architecture. They have called the encoder path is nothing but a contractive path, and they have also called this decoder is nothing but expansive path. And the kind of architecture, right, which they proposed looks like this, right? Looks like this. And now you can imagine why the name is so called a unit architecture, where this part is contracting path, left side part or encoder, and this path is decoder. You will find a lot of difference compared to the FCN and SegNet. The major difference you will find here is this connection. This was not there. Although this part is encoder, this is again the mirror of this decoder is the mirror of encoder, but here they are not storing the pooling indices. They have introduced something called as again the transpose convolution. They have used same number of stages, right? Similar to the encoder, but what they have introduced is nothing but this skip connection from the encoder to the decoder, which will preserve this spatial information, helps in accurately performing segmentation. You can also implement unit architectures without skip connection, and with skip connection, you will find the difference. What is the need of the skip connection from the encoder to the decoder? You can see initially in the original architecture, they have actually used on-padded convolution. That is why they have got a different size output map at the right in the decoder, especially the output. But later people have used padded convolution to get right the output exactly same as the size of the input image. That is what we are also expecting in most of the scenarios. Fine. And in addition to that, they have also proposed some other things, how to deal with overlapping objects, how to deal with, how to use the segmentation, augmentation approach and all, right? And the paper was published in MICA. You can see over here, MICA is one of the top tier conference in the field of medical imaging. Also ranks, also it has, also it holds a very good rank, right? So this is actually the paper. If you can go through this paper, you will find this paper itself is cited more than 1,15,000 times, right? So that means it has been used extensively across different tasks. So not only it is used for the segmentation task, but also for image reconstruction task, where there is a need of reconstruction of the image, you will find its application all the time, right? Unit. And the major contribution they have made is just how to use the skip connection from the encoder to the decoder. If you see, the encoder here consists of multiple stages, and these are nothing but, right, this is, let's say, an input. There are two convolution operations over here, followed by a max pooling operation. Very, very important. I'll show the demonstrations in the hands-on session, right? And followed by another stage. Again, there are two convolutions followed by a max pooling, two convolutions followed by a max pooling, two convolution followed by a max pooling. Very similar to the architectures VGG you have seen. So that means in the encoder, you can also use any classification network. In the decoder, what you are, what you can observe here is, you can apply the transpose convolution. You will get some output. You are not only using this, as an input to the further convolutional layers, you are also taking the output of the corresponding encoder layer to preserve this spatial information. You can say localization information, and then you are combining whatever the output you have got in the corresponding layer in the encoder, as well as the output which you have got from the previous decoder layer. You are concatenating them, passed it to the convolutional layers, right? And finally, what you are getting is the output. And finally, you'll be having one convolutional layers, 1+1 convolutional layer having C+1 number of channels, and it will remain same for all the architectures, as I mentioned earlier, right? It's the most important architecture. Then you will find the variants of the unit architectures, right? Then how people have contributed or how they have designed the variants of the unit architectures. People thought of introducing the residual connection, right? So people have also found that yes, ResNet plays a very, very important role in solving variety of classification tasks, and also people have identified the role of the residual connections. So what they did, they introduced later, right, these skip connections, right? Let's say there are two convolutional layers over here. There's one convolutional layer, there's one convolutional layer, and they just introduced a skip connection over here, right? After at each stage, they have introduced a skip connection, and they have just called it as a res unit, that is residual unit architecture. You can see over here, right? So you can see over here, this is the input over here. The representation may different. Previously, it was looking like this. Now it is looking like this, right? Now this unit architecture is looking like this. So what they did, basically, you can see over here, there's a convolution operation, there's a convolution operation, and there is a skip connection from here to here. At every stage, you will find there is a skip connection, right? There's a skip connection. Right? That means they are trying to just preserve, or they're trying to just reuse the feature whatever they have obtained in the previous layers. At the same time, it tries to reduce the vanishing gradient problem, right? So, that is how actually people have developed a residual unit architecture, just by combining the strength of the residual learning and the unit architecture. Later, people have introduced, right, convolutional layers along the skip connections. That means here people have introduced skip connections, convolutional layers. And also people have also introduced some connections like dense connections and some other connections over here. And they have just given the name it as unit plus plus. You can see over here, right? And they claim that yes, right, they are getting better performance compared to the unit architecture for some specific applications. So again, in 2017, there's a paper called as Pyramid Scene Parsing Network, published in CVPR, the top conference in computer vision, right? Where they claimed that FCN and its variants, right, and some other architectures would not able to handle few complex problems that are inherently present in some of the complex segmentation tasks, right? That means FCN mostly failed to correctly segment small objects and big objects that are present in an image. That means it doesn't have that multi-scale feature learning capability. So then they thought of introducing something called as a pyramid scene parsing network, which consists of something called as a pyramid pooling concept, right? Or pyramid pooling module. Basically, they designed to extract the features at different scales, from the coarse scale to the larger scale, right? Or to the broader scale. So how did they perform? How did they perform this pyramid pooling? What is pyramid pooling here? And what they did? Initially, what they did is they applied or they passed through their input images through any pre-trained CNN architecture like ResNet, and they got their outputs, and then they perform something called as pyramid pooling concept over here. You can see over here, there are 4 different types of outputs. That means they have applied the pooling 4 times. This is an output, this is another output after applying some pooling operation, this is another output after applying some pooling operation, this is another output after applying some pooling operation. The first one looks like, so let's say this size of this feature map, right? Whatever they've obtained from the convolutional neural network is H cross W cross C. What does it mean? They here H denotes height, W denotes width, C denotes the number of channels. And this particularly, right, this output is nothing called as 1 cross 1 cross C. So then how to get this output? Just by applying a global average pooling. We also discussed yesterday. So this global average pooling will help us in reducing, right, the dimension from H cross W cross C to 1 cross 1 cross C. You will get a C dimensional vector over here. That means for every feature map or over every feature map, you are applying a global average pooling. That means for every pixels, you will get a single value corresponding to the every we can say every channel. So what you will ultimately get is nothing but 1 cross 1 cross C. And again you are applying some other types of pooling operation over here, different types of pooling operations to get 2 cross 2 cross C, 3 cross 3 cross C. You see different types of outputs, and then 6 cross 6 cross C. It may be H cross H, H cross H, W, C, doesn't matter, but the output which you are getting is nothing but of different shapes after applying pyramid pooling. That means you are trying to extract features or trying to capture the informations at different scales. Fine. Next, you can see how actually they designed the whole architecture known as PSNet, right? That is Pyramid Scene Parsing Network. You can see over here, this one we have just now discussed. They have initially extracted features from the pre-trained CNN architecture, applied a pyramid pooling concept, followed by 1 cross 1 convolution. Each pooling output is followed by a 1 cross 1 convolution to reduce the dimension, let's say from C to CY4. Why? Because after that, what they did is they used to concatenate the outputs. If you are not reducing the dimension, right, from C to CY4, what will happen is you will get, after concatenation, you will get the number of channels 4 times than the original one. They want the number of channels should be same, right, as the original, which is nothing but C. Right, so that is why they have used here a bottleneck layer after the output of each of the pooling layer. That is what is 1 cross 1 convolution, C by 4 times, and what they have got is this kind of output. And later they have just applied a bilinear interpolation operation. They have not used transpose convolution here. They have not even stored the pooling indices. What they did is they have just applied a bilinear interpolation technique here, right? Just not to introduce more parameters, right? In case of transpose convolution, which we've seen, bilinear interpolation they have used to enlarge the size of all this, right, feature map from 2 cross 2 cross C to H cross W cross C. From 1 cross 1 cross C to H cross W cross C. From 3 cross 3 cross C to H cross W cross C. And then you can concatenate. H cross W cross, actually it should be 2 cross 2 cross C by 4 to H cross W cross C by 4. But after concatenation, what you will get is H cross W cross C. And of course, at the end, you'll be having 1 cross 1 convolutional layer with C plus 1 channels. And you know why we are using this. Always there will be one 1 cross 1 convolutional layer at the end with C+1 number of channels, right? This is all about the PSP network, very, very popular. After that, you may find, right, something called as a deep lab, which is even very, very popular. But you can easily understand the concept of, deep lab now, because just now we have discussed about something called as pyramid pooling, and the same concept you will also find in deep lab architecture. Deep lab is a very popular segmentation algorithm. And it has a lot of different variants, right? V1, V2, V3, and like this. Attention mechanisms we have discussed in the last class. People have also introduced, right? You can see in 2018, when this squeeze and excitation and other kinds of attention came into the picture, people just tried to introduce these attention mechanisms, right, into the unit architecture, call it as attention unit architecture, which will, whatever the features they have learned, right, we will try to focus only on the important features or salient features and suppress the irrelevant features in an input image. You can see over here, this is the attention get. So people have also introduced attentions in the encoder, also in the decoder, and they have also proposed different variants of the attention unit based architecture. Still people are working on it. Res unit plus plus is another architecture, right? Where you will find the application of residual connection. This is residual connection. And this is what is known as squeeze and excitation attention, which we discussed yesterday, which is a kind of channel attention. We discussed. You can see the applications of squeeze and excitation, right? Attention block in the residual, you can say res unit plus plus architecture. So what they have done, initially it was not called as a res unit, and people have just introduced something called as excitation attention block, and there is something called as ASPP here across, you can say pooling, right? Especially this is a pooling layer. You can say for multi-scale pooling and all, right? Pyramid pooling. So this is how actually the architecture of RISC unit plus plus looks like. And then people have, right, there are several other variants are also available in the literature. I cannot cover all these things, right, within 1 hour. Fine. So if you want, you can just go through all the architectures. I hope now you can understand any architecture of segmentation, right? Because you know what is happening in segmentation, how to understand the encoder decoder architecture, what is the meaning of 1 cross 1 convolution at the end of each of the segmentation architecture or segmentation network. We all know that, right? The limitations of the convolutional neural network. Convolution is itself is a localized operation. So that means it cannot capture the most important global information that is present in the, or we can say the global dependencies that is present in the feature map or that is present in the image, right? Although attention have helped the convolutional neural network model to improve the performance, right, to some extent, but it cannot still capture the global dependencies that is present inside the image. So therefore, this VITs or vision transformer came into the picture, which is effective in capturing these long range or global feature dependencies with the help of self-attention mechanism, which we discussed in the last class. But VITs are, you can say, very heavy models that demand huge amount of parameters, and due to which the computational requirements by the VIT models is really high. So that means also we need huge amount of data to train those kind of models. But in case of many problems like medical imaging and all, it is difficult to directly adopt this vision transformer because of the less amount of data, right, in the data set available, especially in medical imaging domain. At the same time, VITs, right, the vanilla VITs, especially the traditional VITs, cannot extract the local information which CNN can extract easily, although it is very good at extraction of the global features, right, or global context from the images. So then people thought, why not to combine the CNN and VIT together, right, to capture both local and global information. I hope it is clear what I'm trying to say. This part again will be discussed, this VIT and the self-attention in detail tomorrow by Professor M.K. Guya from IIT Guwahati. And this is the first architecture you can see that has been proposed, right, to solve image segmentation based on the transformer concept. But the design architecture is similar to the unit right, architecture. You can see over here. This is the first architecture that was published in a top conference, WSEV 2022, right? And you can see over here, this unit R works with, you can say, patch-based concept, where there are a lot of patches, right, that has been extracted from the images, input images, then sent to the linear projection, and there is a position embedding, of course, here, and to this transformer decoder, there is a encoder, and there is a decoder here, right? Because decoder is very, very important over here. You can see the whole architecture of the unit here. So this is the input image. First, they applied a transformer encoder over here to deal with the patches, and then in the decoder, you can see over here they have used some convolutional layers, right, to capture the why they have applied actually transformer over the input images, just to capture the global dependencies, or you can call it as long range dependencies from the images. And you will see its performance compared to the traditional unit architecture. But this architecture is kindly, you can see the input is here of many dimensions. That means the kind of the input which on which actually this unit R was developed is nothing but a 3D volume, right? 3D MRI volume or 3D CT volume. You can say 3D MRI in this case, right? 3D MRI, because MRI is by default 3D in nature. So you have to think about applying 3D neural network here, 3D convolutional neural network to solve the problem, right? Even the filter is going to be 3D over here. So you can see there are some deconvolutional layer, convolutional layer used over here. And there are also few convolutional layer you will find. These are convolutional layers you will find at every stage. Right. So again, the architecture, right, is nothing but the design is based on the unit architecture, but the concept that has been used is nothing but transformer over here, and this the architecture name is unit R. Trans unit is also another type of you can say architecture, or you can say the conv-VIT architecture. You can say convolutional vision transformer based architecture, where instead of taking the patches directly from the images, what they proposed is, again, it is a very recent paper. You can say TransUnit has got a lot of attractions from the researchers, where you can see they have initially used a convolutional neural network to extract the patches, and then they applied a transformer layer over here. You can see over here, first convolutional layers, then transformer layers, and then whatever the output they are getting from in the decoder, right? After using these upsampling operations, right? From the decoder stages, they are concatenating that with the output of the convolutional layers, right, to have both local and global information together. And that's why they're getting better performance compared to the other architectures that has been proposed just before TransUnit. That is what they have claimed in their paper. Codes are available, fortunately, for each of the architectures. So you can just use the pre-trained architectures, whatever is available, or if you want, you can also run this model from the scratch on your own problem statement. Fine. So yeah, this is all about all the architectures, whatever I have already shown you in the evolution. There are a lot of variants. Again, I can say you will find in the recent literature based on CNN and VIT, right? And there are the loss functions that has been used extensively for solving this task is known as binary cross entropy, weighted cross entropy, balance cross entropy. If the classes are mostly the data set is imbalanced, right? You can just go for weighted cross entropy or balanced cross entropy to deal with those kind of problems, including the focal loss. Also, other types of loss functions people have developed over the years, known as dice loss, because the kind of performance metrics which we are going to use in this case is something very different. The two very popular, right, performance metrics that are used to evaluate any performance or any segmentation algorithm is known as dice coefficient and Jaccard coefficient. You can see over here the dice coefficient basically measures the overlap between the ground truth and the segmented image. So you'll be having a ground truth image, right, which is given to us, the masked image, and you'll be getting some output or predicted segmentation mask from your model, and you want to just compare these two, right, the ground truth and the predicted one among these two, right? You want to predict. So dice coefficient and intersection of a union, where you can just find out the regions, whatever you have identified. Thus, you can take the common region between these two and divided by the the union of these two regions. Like this is the ratio between the region that is shared by both the ground truth and the predicted mask, right, relative to the union of the predicted and the ground truth mask. That is intersection over union. So very, very important. Based on this also people have designed some loss function known as IOU loss, dice loss and all, right? You will also find a lot of other variants of loss functions people are using over here. There are a few case studies which I would like to highlight here, right, which we have been working on since last 2-3 years. One is polyp segmentation. What is polyp? So you might have heard about something called as a colorectal cancer, right, which is the third most common types of cancer across the globe. And this colorectal cancer actually originates from a tiny benign bunch of cells, or you can say a tiny growth that is formed in the inner walls of the colon. That is what is known as polyp. Right? You can see over here, these are all right, the polyps. So these are like polyps. You can see over here the growths that are found in the inner wall, right, of the endoscopy images. But why its detection is very, very difficult? Why there is a need of polyp segmentation? Why do we need to design, right, the architectures to identify the polyps? What are the major problems that the doctors, right, or let's say the clinicians are facing? The miss rate is in this case is really high. It is 6 to 27%. That is a miss rate. That means the polyp miss rate I'm talking about. Because of the camouflage properties of the polyps, because the polyps are not visible all the time, the boundaries of the polyps, if you look at, is not, I mean, it is indistinct. It is not clearly visible. It is sometimes, it looks sometimes very similar to the background. So sometimes it is very, very difficult for even the clinicians to identify the location of the polyps. If you cannot locate the polyps carefully, so that may lead to some type of cancer known as colorectal cancer. It has to be detected and removed properly. So to remove the polyp properly, so we need the accurate boundaries of the polyps, right? So accurate boundary of the polyps is sometimes very, very difficult because of the high similarity of the texture of the polyp with its background. Sometimes it is covered with mucosal folds and blood. It is not visible. Sometimes there are multiple polyps that are present. If one of the polyps are missed, then that might lead to some of the cancers. So how to deal with this kind of problem? So then people thought of why not to design automated CNN-based or convolutional neural network or deep learning-based segmentation algorithm to identify the polyps. So there are a lot of papers you will find, very interesting area to work on, right? Because it is also useful for robot surgery and all, right? Now we are also collaborating with some of the even companies, not with the hospitals. I mean, including the hospitals, we're also collaborating with some of the companies where they are planning to develop something, a product, right, through which they can detect, right, this kind of polyps, which are very, very important, right? So in this direction, we have worked a lot and we have contributed, or you can say we have designed several architectures. So one of the architectures which we have designed is nothing but called as multi-scale convolutional transformer network with one of my master student, Niladri. And this paper was actually published in 31st International Conference on Image Processing, one of the very oldest and very reputed conference in the field of image processing. And this paper is also been highlighted as top 5% papers across all the accepted paper in this reputed conference, right? So what was the concept in our architecture? You can see over here, the architecture is again, the design is unit, right? The design is unit based, but the kind of, you can say, we have just designed some simple modules to solve the problem. So in the encoder part, we have not introduced any transformer-based architecture or transformer-based module. In the decoder, we have introduced a transformer-based architecture, or you can say transformer-based module. You can see over here, where you will find a modified self-attention block. And this modified self-attention block, as I mentioned in my last lecture yesterday, where I have mentioned that similarity score, especially, right, is computed along the spatial dimension, right? SW plus SW, remember, and also we introduced here to find out the global dependencies along the channel dimension, not only in the spatial dimension, but also in the channel dimension. That is the major contribution here. We are considering both and combining them together, right? And the self-attention, with the self-attention, we designed a transformer layer, which we have introduced in the decoder. In the encoder, if you see, we have just proposed one multi-scale feature extractor block with the help of separable convolution, which I mentioned earlier. So separable convolution helps to reduce the parameters significantly compared to the traditional convolution, which we usually solve using 3x3, but separable convolution tells us that this kind of convolution can be broken down into two parts, two one-dimensional filters. One is 3x1, one is 1x3, right? And the outer product of these two particular filters should be equal to this 3x3 filter. Then only you can consider these two as the separable filters for us, right? So in this case, the total number of parameters will be 9, but in this case, the total number of parameters will be 6. So this is how actually you can reduce the number of parameters. Again, we have introduced multi-scaling concept over here. You can see multiple filters are applied. Filters having different sizes are being applied to extract information at different scales because the polyps are of different shapes, right? It varies significantly in shapes, size, and colors as well. And then we have introduced something called as a global, you can say, cascaded attention block. I'll show you the demonstration also of this cascaded attention block. So initially we applied a channel attention over here, you can see, followed by a spatial attention in sequence, right? This is known as a cascaded attention block, very simple. And these two blocks are repeated across the encoder stages. And then the decoders, we have used this transformer layer, right? And then together you can see we have used the concept of both convolution and transformer together. The name is so-called convolutional transformer network. The code is also available. If you want, you can just go through our paper. You will get a lot of details about this one and how we have developed, what is the major motivation, right, behind design of this particular architecture. Here is some of the results, quantitative results on some of the benchmark data sets, and we have compared with unit, SegNet, and the almost all the architectures which I discussed today, right? REST unit, attention unit we discussed, REST unit plus we discussed, unit R also we discussed, right? So these are some of the architectures which we implemented on the benchmark data sets and found that our model is performing better compared to others quantitatively, of course. And let me show you some qualitative results where you will get to know more about the performance of the model which we have obtained, right, using this MCT net. You can see over here, these are some of the input images, right? These are input images taken from different data sets, and this is the ground truth provided by the doctors. The last, right, the results that are provided in the last column are nothing but the ground truth with respect to each of this image. You can see there are few cases, especially here, right? Particularly for this example, if you see, there are two polyps that is present. So one polyp is a little bit visible, the other one, that not all the growths are polyp, which may lead to the cancer. You need to only identify that growth, right, which may lead to, or which is polyp, and that may lead to colorectal cancer, even more difficult sometimes, right? You can see this is the output by our model. You can see the boundaries, especially the boundaries, whatever we have obtained is very much accurate to the ground truth, whatever the doctor has provided. Boundaries of these two polyps. You can also look at other examples, like the last example. Boundaries are very, very important, as I mentioned, to remove the polyp, to resect the polyp, right? So you can see the boundary informations are better compared to the others. Compared to the others, I mean, these are actually the outputs obtained by other algorithms. You can see the outputs of other algorithms and the output of our algorithm compared to the other algorithms. It's very close to the ground truth. You can also similarly consider other examples and find the relevance of our model. Although these models have obtained good performance on seen data sets, but its performance, generalization performance is still limited. So when it is applied to some unseen data set, right, that means on the data set on which it has not trained, and the data set which has been collected from different demographic regions using different imaging devices, it sometimes doesn't give good results. That means the generalization performance of these kind of models are still not good. Recently, one architecture, very, very important for all of you, that a segmentation anything model has been proposed as a foundation model for the image segmentation. But it has not been designed for medical imaging task. It is designed for natural image segmentation task. So it is very much well known for its impressive zero-shot generalization performance. I'm not going to discuss much about zero-shot here, but because for zero-shot we have a separate session, right? One of the speakers will discuss about what is zero-shot learning, what is few shot learning, what is one shot learning, everything will be discussed in detail. Then you can correlate with this. But generalization performance, the performance of the model on the on-scene data that is captured using different device captured from different demographic regions. That is what we always want. If the generalization performance of your model is good, then now it is ready for the deployment. But this doesn't happen most of the time. We know that it always works well on the scene data set, doesn't work well on the on-scene data set. So the SAM is very good at performing, right, well on the on-scene data. But we tried to apply SAM for solving the similar task, right, whatever I've shown right now, but we faced a lot of issues while applying this. So initially we applied SAM into the problem statement polyp segmentation, but we didn't get correct output. The performance was very, very low. Why is it so? Because due to the lack of domain-specific knowledge. Even what we have seen, the SAM has already been designed. We were using the pre-trained SAM model, but still the pre-trained, even fine-tuning of, because fine-tuning is required because the data is different, right? It was the target task and the source task is different. You need fine-tuning. We discussed yesterday in the transfer learning class, in the transfer learning session, right? So we need to fine-tune the model. Even the fine-tuning of this kind of foundation model takes huge amount of time, right? Even memory requirements are really high. So then what it will do? Even the transfer learning may not help us here because the transfer learning may take even long time. So then what is the solution here? Then we thought of why not to introduce a adaptive-based learning concept to solve the same problem. Because it is having good generalization performance and we want to use this, so we thought of introducing an adapter-based learning process. Those adapters are very, very important here. So instead of training the whole backbone or the SAM encoder and the SAM model, what you can do is you can only focus on these adapter modules with which you can inject the information to the SAM encoder. You can see over here, the SAM encoder itself is frozen here, right? But what we are training is only the adapter module. And the kind of adapter module which we proposed is known as a Mamba prior adapter module. You can see over here. I'm not going to discuss much about it, right? The Mamba and all, because Mamba is nothing but a state space model. We have a separate session, will be delivered by Badrinaran Patro from Microsoft. We'll be talking on this state space model. You will be getting to know about this Mamba. Very, very Vision Mamba. You can say it is just an alternative of the Vision Transformer model, right? Which is also useful in capturing the long-range feature dependencies at a linear cost or at linear complexity. That is why it is very, very popular. And we have not only used this Mamba, but also we have introduced something called as a multi-scale spatial decomposition to capture the information at different scales because polyps are of different scales. At the same time, we have used this Mamba 2 times by applying saliency pool and context pooling operations just to enhance the feature learning capability, right, by the adapter. And then the adapter will be used to inject the information to this. This is not only the one contribution which I've made in this, because the SAM models are prompt-based and decoder, right? So in the decoder, it is nothing but a prompt-based decoder. It always demands, but prompts are not always available in the form of bounding box and all. It is not always available during the inference time. Then we thought of why not to introduce or why not to design the prompt by ourselves, right? So then we designed some pseudo prompts, and the training, what is happening over here, right? It is a two-way training process. Please go through this paper. Codes are available if you want to, you can say implement. If you want to use this architecture for solving your task, you can also easily solve this kind of problem. And this is published in this year. WACB, as I mentioned, WACB is one of the top tier conference in the field of computer vision, right? I also have seen, where UNet or TransUNet were published, right? So also we have modified this architecture later a bit to deal with some of the boundary issues, because boundary is very, very important in case of polyp. So you can see here the results, whatever we have, got compared to, on the scene data set. That means we have taken, we have trained the model on these data sets, and we are testing the model on these data sets, right? Not the samples are same. Testing samples and training samples are different only, but still seen means the model has seen the samples of this class during training, The model has seen the samples of this class during training, and these are some of the architectures. See, unit is at the top, right? That's the oldest architecture which we compared, and this is the recent approach published in 2024. These are all published in 2024, right? You can see over here, and there are several. These are all like benchmark models available, and you can see the results here. The red color indicates the best results in terms of mean DI score, mean IOE score. You can see some of the results. Not all the time we are getting best results, but these are results which are very, very interesting. On the on-scene dataset, you can see most of the time we are getting better performance compared to the others because of the, because it's the capability of the SAM, right, to generalize well on the dataset. And we have just used this Mamba and this adapter concept to easily train those models, right? And you can see these are very complex process even for the, that is why the miss rate is very, very high. If you look at this image, it is very difficult to identify where is the polyp. If you look at this image, so definitely your focus will go to this polyp, not with this polyp. So again, there's a polyp over here. You can see this is the output, this is the ground truth provided by the doctor, this is the output provided by our model. And if you check, most of the models, most of the recent models could not able to identify the second polyp, right? But our model could be able to identify the second polyp, which is really interesting, right? And on the on-scene data set, that means these are the data sets. The model has never seen a single sample from this data set collected from different demographic regions, and it has been captured. These images of this data set have been captured using different different imaging devices, right? You can see there are some you can say, samples, especially this sample. If you look at, you will not able to find any polyp over here. It's very, very difficult where there is a growth here, right? It is very difficult to identify the polyps, but actually there are two polyps lying here, and our model could at least able to give, little bit, not exactly correct answer, I can say, but this polyp is not giving correct answer. That means in some of the cases it is not able to provide us the accurate boundary information. That's why we have, just now, I think just before a few months, we introduced another architecture, right, which is known as, we have introduced actually a boundary distillation module into this architecture only, and that paper has been accepted in MICAI, where UNET was published, right? We have just got a paper in MICAI where UNET was proposed. I already mentioned you, and you can also go through our the recent paper to get to know about, right? The codes are already available. You can also check the kind, what was the idea and why we have motivated to introduce something called as a boundary distillation module. Fine. So yes, there are a couple of such case studies we have. Another kind of problem which we are solving is diabetic retinopathy multi-lesion segmentation. So these are the problems where the number of class is only one, either that belongs to the polyp category or otherwise it belongs to the background category, right? And these images are nothing but these images are nothing but, you can say, the superimposed images, right? But if you look at these images, let me directly jump to the kind of problems which are solving. This is a retinal fundus image I've already shown you earlier, and these are some of the lesion regions. But there are multiple types of lesions we have. You can see the lesions are of four types here. It is one is soft exudate, hard exudate, microaneurysms, and hemorrhages. There are four different types and different, but denoted using four different colors. And you need to identify all these, you can say pixels, which belongs to the lesion areas. Very, very difficult, this kind of problem statement compared to the previous one, right? Because here the lesions are of even very, very small, even 1 pixel sometimes, there is nothing but a one lesion area. Very, very difficult to identify this. And it is a multi-class segmentation task, right? So, but recently we have developed one architecture. You can see the kind of results which we were getting, right? We can look at this particular, let's say, area or region where you can see this is what the result which we are getting. And if you look at the result by the state-of-the-art approach, is something very different, and our scene is more close to the ground truth, right? So I think yeah, the architecture is not available here because the paper is still under consideration. Okay, fine. So another couple of examples, right? Complex examples you can see over here. This is how the input image looks like. This is how the output image looks like. That means the ground truth look like. And this is the output which we have got. You can just focus on this particular part, and you can see the difference of our approach with the other approaches compared to the ground truth, right? How accurate our model is, right, in identifying the boundaries compared to the others, especially these regions, right? This region is a hemorrhage area, right? Fine. So there are a lot of challenges which you'll find as of while designing this convolutional neural network or vision transformer based, you can say, segmentation models. Couple of problems you will find. One is the lack of large training sets, right? You will be not having much amount of data compared to the classification, because annotation itself is a very, very difficult task in this case, right? So the xi and yi are both are images in this case. So this n is not going to be very high, right? As in case of classification task. So there are multiple ways to deal with this. You can think of applying data augmentation, think of applying transfer learning approaches. Annotation and labeling of the medical images are very, very difficult. You can think of applying supervised learning techniques, right? Sometimes the annotations may not be given accurately, right? So because this kind of annotation is very, very difficult, which I've shown you, right? So annotations, right? These pixel-wise annotations may not be given all the time. But if I ask the doctor just to identify, tell me where exactly the hemorrhage is present, the doctors may tell you this is the region where, this is the kind of bounding box is very, very easy. But accurate, pixel level annotation is very difficult to meet. But we need Y of this kind to solve the same, supervised semantic segmentation models and all. So how to do this? It's very, very difficult. So you can also think about designing some efficient models. You can think about applying or exploring the domain adaptation technique to address heterogeneity and generalizability problems. You can think of exploring and adapting foundation models like SAM, which I have designed, which I have shown right now. Lack of transparency and interpretability. We have also seen shown in our paper. Why is our model performing well? Why there is a need of decoder model, why you have introduced a decoder model. So you can also demonstrate visually, you can prove visually the interpretability or the explainability of the model, why there is a need of those kind of modules in your architecture, and how it helps in improving especially the detection of the polyps, or you can say the detection of the objects that are present in the image. One thing which I have not discussed is how to solve, instance. There may be some questions because of the limited time. I could not able to discuss how to solve instance segmentation. I'm just giving you the idea here. How to solve instance-based segmentation task, and one is panoptic. We have already seen these cases. Instance-based segmentation is very close to a problem statement known as object detection, which is not yet discussed. It will be discussed, right, by Professor Aditya Nigam from IIT Mandi. So then you can easily correlate. So what you can do, so you might have heard about something called as first RCNN. First RCNN is such an algorithm which is very popular for solving object detection. So the instance segmentation is like that only. So you need to identify instance segmentation. You still remember, I think, if there are 3 dogs, so the instance segmentation, right? If there are 3 dogs, the semantic segmentation will only highlight that all are dogs, nothing else, right? But the instance segmentation will say, this is dog 1, this is dog 2, this is dog 3. First, you need to identify actually where there is dog, and then you can apply FCN kind of algorithm within this box or within this ROI to identify the dog or the boundary of the dog. You can say the shape of the dog, whatever. This faster RCNN is going to be very, very useful for solving this instance-based segmentation task. So you will first apply the faster RCNN, and then you will apply this faster RCNN with FCN, which we discussed on the ROIs. What is ROIs? These are ROIs. These bounding boxes, this region of interest. You will apply. First, you will apply a faster RCNN to identify the regions where there is object, and then you will apply FCN. This is the simplest way to solve instance-based segmentation task. I'm just giving you the idea, right, how to solve this. You can also modify the algorithm, and you will also find a couple of algorithms that have been proposed over the years. What about the panoptic segmentation? People have applied, FCN. People have also applied, in the input image I'm talking about, a mask RCNN. Actually, we call it as a mask RCNN. For instance-based segmentation, mask RCNN. This is actually the name of the algorithm which is used for instance-based segmentation. Fine. master RCN with FCN on the ROIs. Mask RCNN for instance-based segmentation. FCN you can apply over the image to get semantic segmentation. Just fuse the results of the semantic segmentation and the instance segmentation, which we have obtained from masks RCNN and FCN, to get the output of the panoptic segmentation. I hope you got my point. What is panoptic segmentation and what is instance-based segmentation, and how to solve this kind of problems with the idea of both instance segmentation and semantic segmentation together. Right? So I'll stop here. So if you are having any queries, please write it in the chat box. I'll try to answer. Okay, I think there are a few questions. So please explain panoptic again. Dr. Parul, is it clear right now? Panoptic, I think I discussed a couple of times. Okay, thank you so much. From Dr. Pooja, sir, let's say adding transformer blocks and residual connection into unit model. Okay, will it be considered as a noble work? People have done it actually. So see, transformer blocks always comes with a residual block right now. And there's a very recent paper, right? You will find very interesting paper that the analysis of the importance of the residual connections in transformers or in self attention, right? That is like always residual with self attention. I don't remember exactly the title of the paper, but always you will find transformer, right, along with the residual block only. So you may think of designing something called like I informed you that yes, a transformer, Mamba is nothing but an alternative of the transformer, right? So you can also think of using Mamba block in place of transformer, or else you can think of designing your own transformer block. That means you can think of combining both, let's say, convolution along with the transformer. You can think of exploring the transformer in multiple domains. That you can do. Will be considered as a noble work. ACI journals don't consider hybrid models. Yes, of course, nowadays, right? So that also you need to identify. Even let's say you can think of designing self-attention module with lesser number of flops and parameters, right? So example, I can give you one idea. Let's say, what I have discussed yesterday, that to get query, key, and value projection, we usually apply 3 times 1 cross 1, right? So what you can do, you can apply 1 time 1 cross 1. Obviously, the number of parameters is going to be very, very less. And you can share the output with query, key, and value, right? That is what you can do. But you can also check whether it is giving similar results or not. If it is giving similar result, then you can also remove unnecessary 1 cross 1 convolutions that are being used for getting different projections like key, query, and value, right? That can be shared. That can be shared. Okay. When, okay, I think you can explore other things. Okay, fine. When we talk about data sets should be large medical, how large they should be, it is a very difficult questions, I can say. The more, the more image you can pass to the deep learning or this kind of foundation models, the more reliable result you can expect from them. But when I say it is large, of course, it should be, like, ImageNet, which is most of the times not possible. You know that even in medical, imaging, if you are having more than 10,000 images, even for, it is like for segmentation, even if it is 1,000, even 5,000, it can be considered as a larger one, because it is very difficult, right, to get such a large data set. But yes, nowadays, because collection of the images, previously it was difficult. Now it has become very, very easy, right, with the availability of those machines even in the small towns and all. So collection of the medical images has now become very easy. but the annotation is very, very difficult. Still, we can't annotate. We cannot annotate the medical images, right? Even if you are thinking about, semi-supervised learning where you can plan to give some pseudo levels, but yes, we need at least I know a few number of samples, at least a large number of samples, which must be annotated. Sorry, Aditi. From Dr. Aditi, sir, for the classification recognition task, we can just use encoder. Yes, absolutely. Absolutely. So for the classification, the encoder part is sufficient, but for the image reconstruction part, right, wherever you need the image as an output from the convolutional neural network or vision transformer, you must need a decoder architecture, right? So there's no need of decoder in the classification task. Absolutely. Any other queries? Any other queries? No problem. So I'll stop here and I'll start the next session, which is an on-site session just after 2 minutes.